Hi everybody, this is lecture number 2 of the topic number 2. In this lecture, we will discuss the inductors as an energy storage element employed in PWM power conversion circuit. First, we'll review the definition of the inductance and the Faraday's law, which will provide the circuit equation of an inductor derived by the periodic pulse voltage waveforms, and I'll explain the concept of voltage drive, which is closely related with the circuit behavior of the inductor in the switching circuit. To further illuminate the role of the inductor, we'll go through some inductive switching circuits, and finally I provide one conceptual operational scenario to illustrate the inductor as a transitional current source in switching circuit. Next slide start with the definition of the inductance. Okay, so much about the switches, and I'd like to discuss some basic thing, very basic thing about the inductor. This is the inductor. Usually inductor is built by winding some coils around this bar, iron bar, or some magnetic material, okay? And assume we push the current. So initially current is flowing in this direction, in this manner, okay? Then when current changes, then H is magnetic field is developed by some law, okay? So direction of this current and direction of this H field is related with this Ampere's right-hand rule. So this is the direction of the current, then this is the direction of the H, okay? So H is developed. When H is developed this by the current, then there are some steps, and eventually the lambda will be developed. Okay, so here we assume the origin of this operation is this current, IL, and the final result of this electromagnetic behavior is this one, lambda. Okay, so electromagnetic process in the inductor, assume there is initially there is IL. Okay, so current is flowing through this inductor in this direction. Then IL will develop H. H is magnetic field intensity. Okay, so when H is developed, Bt will be developed. It's the proportional constant. It's something similar to Ohm's law. There is a current and there is a resistance. Voltage will be developed, something like that. Okay, and Bt is called magnetic flux density. Unit is Tesla. Unit is Tesla. Okay. And mu is proportional constant. Okay. It's called permeability. It's permeability. So this is the source. And due to this source, H is developed. And due to H, Bt is developed. It's called magnetic flux density. This is the density. And S is cross-sectional area of this core. So cross-sectional area times this density is magnetic flux, total magnetic flux. flux. Okay. Finally, n is the number of turns, and this lambda t is n times this total magnetic flux is called flux linkage. So this is the output of process. Right? So you may think this is the input of this process, and this is the output of process. Okay? So from this, we define the inductance of this inductor. Inductor is name of the device. Inductance is nature of inductor. So inductor and inductance is different. Every inductor has some finite inductance, and the definition of inductance is this is the input to the process, ILT. This is the output of this process. So inductance L represents how effective this inductor to generate this magnetic flux linkage. It's called inductance. So this is our definition. Okay. So you remember this is our definition. We define this for some purpose, for the convenience of us. Okay. So same equation. This flux linkage is inductance times ILT, which is the same equation. Okay. So this is the first equation related with this inductor. There is only one equation here. Okay. There is a second equation which is closely related with inductor. That is called Faraday's law. Faraday's law says the time-varying magnetic flux linkage induces a voltage across the inductor. Okay? Why is that? This is the natural law, is the feature of nature. We don't want to prove this. We observed this. Okay? So everybody is believe this. So this is law. Okay. So let me explain this situation. This is IL prime. Actually, it's better to use notation IL prime. IL prime. IL prime is different from IL. In previous lecture slide, we assumed IL is originally coming into the inductor, but IL prime is something else. Let me explain that. So with this IL in the previous lecture slide, this is generated. This magnetic flux is generated, lambda is generated, and assume this lambda is time varying. It's not a constant. It's varying in time, in sinusoidal fashion or some other fashion. Then voltage will be developed across this by the Faraday's law. We don't know why. Maybe he knows. Okay. Then this magnitude of voltage developed here is just time derivative of change in lambda t, which comes from the HT. Okay? So we know the magnitude of this. So this is a very simple law. Okay? And we select the proportional constant 1 here. We select 1. Okay? So we have this simple equation. So it says when HT is time varying, then the voltage is developed across this inductor in this value, just time derivative of this variation, and the polarity of this is determined by Lenz's law. Lenz's law is this. Okay? So Lenz's law. So this change in this direction was the original one, is the source of this process. Then the voltage will develop across here by this equation, and polarity of this one is such that if current voltage will be developed, then current will flow through this. if there is something is connected in between. So we assume this resistor is this some imaginary circuit. Then with this voltage, the current will flow this in this way or this way, but the proper way of current flow is the flux developed by this current is in opposite direction to this original current. That's called the Lenz's current. Okay? Because the original flux was this direction, then the flux generated by this imaginary current should be this direction. Then means this current should go into direction. Okay? So current should go this direction. It's coming out here and entering to this. Then polarity of this should be plus minus. We are thinking this as the simple battery. So this is the battery voltage source. Then to have this direction of the current, this should be plus minus, not the other way around. Okay? This is the simple law, Lenz's law. So inductor is very simple device. Only two equations are involved there. One is Faraday's law, and the other one is definition of the inductance. And the direction, polarity is determined by this Lenz's law. That's called the Lenz's law. Okay. And this Ampere's right-hand rule. So this one, okay. So if you generate something, use this one, this right hand. If you are rotating something, use this one. Okay. So this is direction of the I. Then H is here. This rule also applies to the find out the direction of the I due to the H. Okay. Here, this is I and this is H, but there is a I. No. There is a H in this direction, then I will be this direction. What I mean is the relationship between H and IL is always determined by this right hand. Okay. So this is basic circuit equation of inductor. We use right-hand rule here because induced H should be opposite direction to this. Then it should like this. Then current will go this direction, so current should come out like this. Okay, it's coming out and coming in this direction based on this right-hand rule. Okay, this one, the same thing. Right, circuit equation. So this is the final result of the previous discussions. So there is a voltage across like this. The current is going into this direction. Okay, this is the same as the conventional Ohm's law. So in Ohm's law, I is coming in, then this is the resistor, voltage developed plus minus is the same direction. Okay. So this should be considered as the original current which initiate this process, and VL is the voltage, polarity of voltage determined by Faraday's law plus Lenz's law. So IL prime is not shown here. Okay? So if you forget about everything, and this is the correct direction of the inductor current, and the proper polarity rotation of the inductor voltage. Basic equation is very simple. This is what? This is Faraday's law. Okay? Faraday's law. And you integrate this, then you have this. Right? And this is what? relation lambda T is LILT is definition of the L. Okay, we defined L as the ratio of lambda T to ILT. This is our definition. Then we use this, and this is the basic equation for the inductor. Okay, so you know this, right? That's one thing. So this is one equation. Okay, this is another equation. If you differentiate this, you will get this. Okay, if you integrate this, you will get this. They're the same equation, but with this is the basic equation, Faraday's law, and this is the definition of inductance. Then put this, and you will have this. Okay? There are only one equation. If you have the inductor, then you have only one equation, this one. Same as this one. All right? There is no rule such like when DC inductor is shorted. That's not true. It does not say anything about that. Okay? But some professor in undergraduate course, they teach at DC inductor is shorted. In AC, capacitor is opened. That is not exact statement. That can be true for some special cases, but in general, there is no rule, no such a rule. Okay? We only have this equation, same as this equation. Okay? So you only have one equation for the inductor, and you analyze all the circuit with this equation. Okay? So if this is the sine wave, you should integrate this or you differentiate this. But we only consider two extremely example case mostly. One is this VLT is constant or VLT is 0. We only consider this for this PWM converter case, which is very fortunate. Okay, so suppose this is DC, then we have equation here. Then this is DC. DC is coming out here. This is DC VS. So we have this. Okay, so inductor is here. Inductor is here. Then DC is applied. Then this is time. Then this will be increased forever linearly with slope of Vs divided by L. This is it. All right? There is no statement, this inductor is shorted. Nothing like that. This current is linearly increasing forever, but in practice there is a mechanism called saturation. Then something else will occur. But here, in this equation, at least there is a DC across the inductor. Then inductor is increasing with this slope. Okay? And the other case is we assume the voltage across inductor is 0. Okay? Inductor is 0. Then we use this equation. So VLT is 0. Okay? That means either L or this one is 0. L is not 0. Then this one is 0. So time derivative of ILT is 0 means ILT is what? Constant. Remains constant. So there are two cases, only two cases, linearly increasing or decreasing or staying the same. Right? So we only consider these extremely simple cases. This is a very simple example. Okay, let me show this. The process of evaluating inductance of this toroidal inductor. Toroidal inductor is this shape is called toroid. Okay, so it usually is ferrite material called ferrite, and we wind turns here and turns here. But you don't want to concentrate your winding only partially here. You want to distribute this evenly, but I used this for the simplicity of this figure. Okay, so there are n turns. Then definition of inductance is this one. Total flux linkage divided by ILT. And total flux linkage is, this is the total flux, number of turns. And this total flux is product of cross-sectional area and BT, right? And this BT is mu HT. This is the proportional constant permeability, like this. So this is the definition of inductance. And there is Ampere's law. Ampere's law says, so there is H, okay? So H is developed. So H, you integrate the H through this magnetic path, line integral. Result of the line integral is same as the current passing through this area. So in equation, this HT times LM is mean magnetic length, is same as the current, entire current passing through this cross-sectional area, which is N times IL, is this. Okay, so we replace H here with this one, then cancel this. This is the inductance of this toroidal inductor with number of turns of N turns, and this structure, cross-sectional area S and mean magnetic path Lm. So this is the law, all right? So mu is mu r times mu naught. Mu naught is this number, is permeability of free space, and mu r is relative permeability. So is for the ferrite, it is several thousand, not infinity, or hundreds, not hundreds thousand, just several thousand, and this is a very small, strange number, okay? Because we select the proportional constant of Faraday's law 1, because of that, I don't know. Then maybe we need some strange number here. Particularly in the magnetics, there are very, very complicated relationship between constant. Maybe that the selecting Faraday's law with proportional constant 1 was bad choice. Because of that, we have very complicated numbers later. Okay. And the next one is voltage drive inductor. Means there is an inductor. We apply voltage source across the inductor. Usually, okay, always, almost always. If you use current source here, the inductor is usually carrying current. Maybe it carries 2 amp. You put exactly 2 amp current, then that is okay. Anything other than will cause KCL problem, but you can connect any voltage source across this inductor. Okay? So if there is an inductor, you are connecting this inductor with voltage source. So for symbolic notation, this current inductor can be regarded as current source, so there is no comparability problem. So there is inductor, we use voltage source to drive that. And this one example. So initially the current was 0, initial current of this inductor was 0, and we put plus voltage, then the ILT is increasing linearly with this slope. Okay, obviously, according to the previous equation, this is the basic equation, Faraday's law, combined with the definition of inductance, because VLT integration, VLT is constant, is VSL. Vs divided by L is the slope and linearly increasing. Okay, and we apply the 0 Then here, this variation of inductor voltage is 0. So VL is LDILT dt should be 0. Okay, VL is 0. This one is 0. Then IL remains constant. If you apply negative voltage, it decreases linearly like this, right? Okay. Here we assumed the continuous voltage source to drive inductor. Now we introduce the switch here. So inductive switching circuit. Here is the inductor and Vs. Okay. Initially inductor current was 0 and it connects to this. Then all of a sudden we apply the Vs, constant voltage across the inductor. Then ILT will be VLT is VST. Okay? So it's constant. So increase like this. So it's shown here. At the time of 0, switch is closed. It's closed and opened. Okay, so T equals 0 is closed, then VL becomes Vs, so current is increasing linearly, and all of a sudden this switch is turned off, then this current collapsed to 0 because there is no path, collapse to 0. Then that change variation in this current will induce voltage like this. The equation of that is VLT is L times time derivative of this inductor current. Here, this one is minus infinity, right? Because we are assuming this current is decreasing, it's changing in negative direction, and this variation, this change is instantaneous. So you have infinity. So we have infinity voltage. This one is minus infinity. So there is a huge voltage across this switch, and this switch will be destroyed, right? So it's not workable, or it works only just once. First it works, it closes, open, and it blows up, all right? So another interpretation of this is the energy stored in this inductor. This is energy stored in inductor, okay, is dissipated abruptly. So that means this voltage spike is destroying the switch, right? So this is not workable. There is a workable circuit here. So we add this diode here. Previously there is no diode. Then switch is turned on, is increasing, turned off, everything blows up. That was the problem. Now we use this, okay? With this switch and this diode, it becomes SPDT switch. Previously it's just MOSFET, one switch. Okay? Here we have SPDT switch. Okay? So this is the switch drive signal. It's a closed, open, closed, open. So when this one is closed, it increases linearly. When this one is open, previously without diode, the energy is dissipated instantly, and switch was destroyed. Now, when this is turned on, this turned off, this current is turning on this diode. Okay, when this diode is turned on, voltage across this diode is 0. That means this current remains here, and next cycle it increases and goes like this, right? So IL is increasing and staying the same, increasing, staying still, and go on like this. So maybe this will work, okay? So, and voltage, inductor voltage here is, during this period, inductor voltage Vs, and this period, voltage is 0. 0 means, this 0 means, this time derivative of inductor current is 0. So inductor current is remaining 0 all the time. No, that period. Okay. Finally, I'd like to show this. I'm using this to explain why inductor can be considered as a current source mainly for the undergraduate student. All right. So initial status of this switch was this one. Initially, this switch was open, and this switch was closed. Okay, that is fine. So this is open. So voltage source is open. That is absolutely fine. And current source is closed. Assume current is 0. So this one is okay. Right? This one is open. Now this is closed and this is opened. Okay? This is closed while it is opened. Then that circuit becomes like this. Oh, not this one. Right. This is something else. Okay? So this is closed. This is open. So it looks like this one. Then there is a loop here, and inductor across the inductor Vs is appearing. So current increase linearly. Okay. So at this T1 moment, this is opened, right? And this is closed. Previously it was opened. It was closed. It is open. Now it is closed and it's open. Okay, that means voltage source stands alone, and this current inductor is shorted, so current remains the same. So during this period, if you have this is what? This is a voltage source. Okay, you have current source as a battery, you have dry cell, you have a voltage source, and you have this loop. Then you are having current source, which is this one, and at the same time you close this and you open this, then current is dissipated through this path. So current is charged to the inductor, and inductor is working as transitional current source. That energy is dissipated during this source. Okay, so with this you can make current source, but very inconvenient to store and to carry. Okay, but conceptually this is same as the voltage source dry cell opened. Okay, right? Okay. Okay, we'll stop here.